We just ate.
Okay, so we'd like to welcome you first of all to the video conference for the MasterClass. We're here at Fermilab, and there's a whole bunch of us here, as you can see. So we'll introduce ourselves. So we'll just go down the table, and we'll have a guest artist coming soon. I guess, Dave, you want to introduce yourself first?
I'm Dave Trapp. I'm a Quarknet fellow.
And Dave is handling the technical aspects and occasionally, well, doing as much as he can to keep me on beam. I'm Ken Ciceri. I'm a Quarknet staff member, and I'll sort of be trying to keep things moving along and making bad jokes occasionally.
I'm Jake Anderson. I'm a research associate here at Fermilab. Work on the CMS experiment. I'm here as the moderator.
And so this other group you see here, they're our team from Notre Dame. So the participants from Notre Dame are actually here at Fermilab today, and we're a small group, so we're going to introduce ourselves. Sophie.
Hi, I'm Sophia Zovich. I'm Sherelle Lucky.
I'm Philip Moss. I'm Mario Estrada.
Oh, okay. Okay, we have a secret observer too, but we're not going to tell you who he is. Okay, and so I thought we could start, as we often do, with just a few questions to get us going. So I'll start with the students in Rochester. So we see you fine. You're looking great. And I have a question for you. So before you came to the video before you started the MasterClass, how many of you had heard of Fermilab? Raise your hands if you had heard of Fermilab before you came to MasterClass. Wow, this is a well-educated bunch. I am really impressed.
Yeah.
And how many of you had heard of the Large Hadron Collider? Almost as many. Very good. Wow. So you guys are a pretty well educated team. So I'll give you a bonus question to work on, and you can answer that question later. Your bonus question is, considering that the circumference of the Large Hadron Collider is 27 kilometers, and the protons circulate at close to the speed of light, about how many times in a second does a proton go around the collider ring? And if someone comes up with an answer, we can come back to you on that. Hopefully right now you're scribbling on the backs of your envelopes. So, okay, so Notre Dame people. Before you started with the RCLC Physics Club, how many of you had heard of Fermilab?
I hadn't heard of it. Man.
I've heard of it.
So,
I go there.
yeah, you said you were here, yep.
You know what it was.
And so our featured scientist has joined us. This is Young Ki Kim, and Young Ki, maybe you could say a little bit about what you do.
Okay, so who else do we have here?
This is University of Rochester, high school students.
University of Rochester high school students. I got my PhD at University of Rochester.
That's right.
Really?
Yeah. So I thought you knew. I'm just kidding. That's why you have. Great. It's really, in fact, that's the first time I ever came to U.S. from South Korea to Rochester to get my PhD, and I thought I came to heaven.
Oh, wow.
It's because in Korea, if you get your PhD or any this kind of the education, you have to pay to get any education and all that. So you go into graduate school and etc. You have to earn some ways to pay your tuition and for living expenses. But in U.S. is a very, very actually generous that you can start as a teaching assistant or research assistant in graduate program, and everything is covered. Of course, it's science. If you go to humanities, it's a different story. But if you're in science, it's all covered. So I came to Rochester and I go, I'm learning, and they pay me for learning and education, and I thought this is a incredible and heaven actually. So I have very fond memory of Rochester.
Do you have fond memories of the winter?
Oh yeah, I mean, winter makes you strong and builds a character. You're so dedicated and determined. So there are so many exciting things going on. So winter shouldn't bother you. So I had actually a very good memory. However, it's talking about what I do and what I've done. So I spent, to be honest, I didn't spend that many years in Rochester. I spent only 1 year. Actually 9 months, 2 semesters. And then I went to Japan, where the laboratory called the KK, that's a high energy physics laboratory. Like in US, it's the Fermilab, which is the only particle physics laboratory, has all the accelerators and facilities for particle physics research. And similar, the laboratories in KK. I mean, in fact, in the world, there are 3 primary laboratories primarily devoted to particles. I'm sure you are very well aware of. Fermilab and KK. So these are 3 really primary national labs. And we have a different kind of accelerators. It's not that you have one kind of accelerator solves all the, or answer all the questions, but you need a different kind. So they're very complementary. And so CERN has one kind, and we have another kind, and Japan has just a different kind. So my thesis analysis or research topic was at the AMI experiment using the accelerator called the Tristan. That's electron-positron collider. So that was in Japan. So after 2 semesters, I was shipped to Japan and spent there for 3 years, and learning English and Japanese at the same time, which is challenging. So that was my education, and then I came back to US, did my postdoctoral program that usually you have to do after you get PhD, and you have a few years of this research experience, and then you find staff scientist position at the lab or going to a university. So I did my postdoctoral program at Lawrence Berkeley Laboratory. It's in Berkeley, in California, near San Francisco, working on CDF experiment at Fermilab. And then after that, I became a professor at UC Berkeley until 2002. So at that time, from Berkeley to doing still the experiment here at Fermilab, so door to door, 8 hours. So you can imagine, one day you teach, next day you come, and you cannot coming back within a day or so. So you have to always use red eye, which is if you do every once a week, you are really, really tired of it. But physics is so exciting. So right? That's how who we are. And then I moved to the University of Chicago in 2003. And I'm still faculty there, but from 2006, I became deputy director of the Fermilab. So we have a director, and then I'm the second person in command. So my primary research interest has been, at least last 10 years or so, is to understand origin of mass. So some of you may have heard of Higgs particle, that is responsible for giving mass to elementary particles like electrons or top quarks, and all these particles, which are the smallest things and building blocks of the whole universe. We call them elementary particles, and they have mass. Some has very little mass, like electrons, and top quark has a lot of huge mass. Actually, neutrinos, these are even much smaller mass than electron, like 6 orders, like million times smaller than electron mass. So it's very, very tiny, but they have a mass. So my main question is, how these particles acquire mass, and who determines that, hey, electron, you have to have this mass value. Hey, top quark, you have to have that mass value. And how this is all determined? That what has been my primary interest. So that continues. So, Higgs is we think it's responsible for giving mass to these particles. And our current understanding, our theory called the Standard Model, does not tell you how heavy Higgs particle is. So that made all experimentalists having hard time to figure out how to find Higgs, because we don't know how heavy that is. But there are a lot of achievements and results came out from the LSC experiments, Atlas and CMS, and also Tevatron CDF and D0 experiments for direct searches for Higgs. But also there are other ways of figuring out what Higgs mass should be in the Standard Model. That's by measuring W, boson particle or tangent particle. Their mass values, if you very, very accurately measure them, they can give some hint on where Higgs mass should be. So those things are what I have been studying. So that's kind of my research interest, and now I'm so excited about neutrinos and all that because it's really cool. You may have heard that one result last year sort of presented that neutrinos travel even faster than speed of light. So that became really hot topic. It turns out that looks like there are some error in the experimental measurement. So, but people are honest when they see looks like neutrinos travel faster than light. A lot of people were skeptical, but these experimentalists, they trying to bang their heads to figure out whether they made any mistakes. They couldn't figure that out, so they put on the table, say, hey, this is as much as we've done. Looks like neutrinos travel faster than the speed of light. So if you have any criticism or anything that we should have checked, just let us know, kind of very honest way. But actually, they themselves discovered that there are some mistake in their dealing with their equipment. Just like how to deal with the cables, whether you plug in properly, or that kind of stuff really influences a very, very important measurement. So, not only when you think about these measurements and etc., big accelerators, powerful beam, powerful detector, often the problem could be caused by a simple thing like you didn't plug it in properly. Of course, we learned, I think our scientist community learned that we have many ways, we have to check all those things. So we all learn as we move on. But so anyway, so neutrinos are very, very fascinating particles. So as the deputy director of the lab, my role is making our future scientific plan for the lab and for this community. And also I have to learn everything. And one thing that I learned a lot from just university professor and doing research, and your mind is that you're always thinking scientist, dealing with only scientists. Although when you build detectors, you deal with engineers and technicians, but your mindset is for science. But with this job, Fermilab, for example, we have about 2,000 employees. 300 are scientists, about 300 engineers, 300 the computing professionals, 300 technicians, and about 300 also people who do a lot of administrative work. And we even have a fire department. So we have to clean snow. Somebody at the lab has to, clean everything what's going on, have to make sure that the buildings are well maintained, and all the utilities and power, electricity to water, everything has to be handled by the lab. So it's like running a small village, like a mayor, and I'm the deputy mayor, vice mayor. So you have to, learn all those things, and you realize that, so much effort beyond, in order to make a science possible, there are so many people behind the scene. Their effort is tremendous, and you really become modest. Hey, you thought about we scientists, and then you realize how much of effort by many, many different skilled people helped so that we can do science. So that's my sort of short, brief description of what I do. But if you have any questions, I'm more than happy to answer.
I thought maybe, if you didn't mind, we look at some data first, and then you can stick around for some questions?
Sure.
So, hold up now. Dave, and so this is the fun stuff, of course, for you as a scientist. That is data. And
Sorry.
oh yeah. Supposed to. Oh, there it is. It's online. Yep, there it is. Okay. So we have some data that's been submitted, and Rochester, maybe would you like to describe how you got the ratios you got and what you think it might mean?
Yeah, so Ken, we actually haven't had a lot of time to discuss the results. So this is actually the first time that the students are going to see it. But yeah, we can go ahead and then describe them. So here on the first row, you have our selection, whether this was a Z or a W, and whether it was positively charged or negatively charged. And then what we've calculated then is also the ratio of whether the electrons or whether the events were electrons or muons. And our number comes a little bit higher than it should be at 1.78, okay? So I think you tend to see a little bit more electrons than muons, so almost twice as much. But it turns out that that's actually okay, because when you add up statistically with the numbers from Notre Dame and Shizuoka in China, the final average comes at around 1. And do you think that makes sense or not? So should the W and the Z events decay equally to electrons or muons, or should they prefer electrons over muons? What do you think? They should be about equal, right? Right, so the consensus here is that it should be about equal.
So, Nate, do you want to comment on why they should be equal, or?
On why they should be equal? So I mean, there's a theorem of lepton universality. So electrons and muons are both leptons in the standard model, and so essentially you should be able to change one for the other, and it shouldn't change anything. There's also a third lepton, which is the tau, but it's much harder to pick out in a collider, and so we don't have you guys picking out taus.
You didn't try.
No, it's especially hard at the LHC, and even some LHC scientists have a hard time with that. So the electrons and muons, but they should in fact be equal because of the lepton universality.
And we also have our W, so Notre Dame had the higher W plus W minus ratio, and Rochester came in at 1.3, which is similar to Shizuoka. And so it came out to 1.34. And I think CMS sees about 1.4 for that ratio. Do you know what Atlas sees, Yoki?
No, I don't.
Okay.
Yeah, I
Yeah, I
looked it
think-
up. It's 1.4, yeah, it's around 1.4.
Okay, thank you, Iran. Yeah, so we're not too far off, and I think the cool thing is we can see how the statistics help out. Notre Dame, any comments you guys would like to make about your numbers and ratios?
Not really.
No?
What about this W and Z ratio? Is that consistent with the
So we
and Atlas sees?
So we didn't do that count directly, and when we bring up a mass plot, well, so we did, we added, in our Z candidates, there are actually some non-Z events, and so that will be skewed.
Okay.
So it's actually a pretty much 10-to-1 ratio in the data, but we have other things in there. Sneak some other dimuon and dielectric candidates.
The number, the 1.49, that was the number we had, right? The one you
Right.
showed us before. So that was, we had more than the norm, you said.
Right.
I think that's interesting because we didn't look at a whole lot of different particles. We looked at actually a little bit less than some people.
Mm-hmm.
So I just found it interesting that the number is actually more than the normal, whereas other people's were closer to the other end.
Right.
Well, Rochester seems to have done a little bit less than we did. even as far as how many W run events.
And Shizuoka did a lot.
Yeah.
So, but that's what scientists do is they put their statistics together whenever they can.
Yeah.
And try to get the best numbers they can.
But we look good on average. Our average is nice.
So let's take a look at the. Oh, I'm sorry, Aaron, you had some comment?
Nope.
Okay. I'm going to bring up, if I can, hold it, working on it. There it is. So this is the mass plot from Rochester, and maybe you wanted to comment on that.
Yeah, so this is again compiling your Z-mass candidates. Remember that it appeared the mass on the right column. And so this is a histogram, which basically is stacking all those on top of each other, okay? So, for example, here you got around 11 entries, around 90, okay? So this bin is basically, the range here goes between 50 and 110, and for example, for the peak bin here, which measures 2 GeV, means that we found 11 events in between 89 and 91, basically, okay? And so this is what you're seeing here, that we found one event, for example, around 52, etc., 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 until you see this big bump around 90. Okay, so if you do the math here, then the mean comes at around 83, but that's okay because we only have around 53 entries. Okay, and so the real mass is exactly around 90, 91 GeV. So we're very, very close in there. And so here you can see these lower tails. And that's because, as Ken said, these events had a little bit of other events going on in there. And I think that's what we're seeing here. When you click this as a Z2 mu mu or Z2 EE, but then actually the mass was much lower than the one coming from the real Z. Okay? So for example, I think there were some events, there with a Jape psi, for example, which is around 10 GeV. And so those are pulling down this tail this way. Okay?
Okay, that's great. Comments?
Yeah, looks very nice. Yeah.
It looks good, yeah.
Nice.
Yeah, that's kind of the way we expected ours to look without the surprise peaks.
Yeah, so they have a surprise because the mass plot goes all the way down to
180. Yeah, we have like.
Made a mistake. What's my email? I do things like that. Okay, so that's what we're doing. Okay, so coming up, there should be the Notre Dame mass plot, and so rely on our panel of experts to speak about that. That's you guys.
Okay, so we got the same peak as you guys did as far as around 91.
Yeah, that's
90, which we calculated to be our Z particle. But we also got a little blip all the way over there at 180. That's about 185. And then we also, 2 peaks near, one is close to 3 or between 0 and 3. That's the J side particle. And then also the one that's about 10 would be the epsilon particle that was snuck in by our moderator.
Yeah.
I guess, so we kind of speculated to say that the one up by 180 was probably maybe a zoo particle or something random that we couldn't really tell what it is.
Did you guys have any?
Could it be photon? Can just decay to electron positron or mu plus mu minus. It's rare, but you said a blip in the 0 and 10, but there's other things going underneath. That's we call virtual photons, not real photon. If it's real photon, mass is 0. But there are these virtual photons possible and allowed, and they can decay to E plus E minus mu plus mu minus, like exactly Z decay. But that does not produce sharp peak like a Z. But I'm very impressed that background is such tiny, such a low mass region. These are data, right?
Right, so, so the data was skimmed for WZ, JPSI, and Upsilon, and then combined into one data set. So, of course, and there was also background in there too. So, not really a Drellion curve or anything like that.
In fact, you're right. If there's a very exotic particle like a Z, but so looks like a Z, but exactly not the same, but could be related to another force carrier kind of thing. It could go really high energy, high mass region, and if you see another bump like that, then you say, there's a new particle we could discover that way. We haven't discovered it yet, but that's how the particle experimentalists are searching for such new force or new force carrier. Yeah.
Okay, so I think both groups came up with interesting results and really nice Z-peak, which is of course the main item on the menu. And that's good for us because that means CMS is seeing the Z where it's supposed to be, which is a relief. So, and we have data, Atlas does the same. So I think it's a good time then to switch to our Q&A mode. And maybe we could start with Rochester. If any of the students have a question for Jake or Young Ki, or in general, fire away.
Any questions? No? I don't see anything around here.
Okay. They better be careful because I'll come up with a question for them.
Yeah, shoot.
That's right.
So, okay, Rochester folks, and I'm sure you're very much aware of this as well. Do you know about the neutrino studies that are going on from the University of Rochester? And raise your hand if you know about the neutrino program at Rochester.
There's a couple of hands showing up.
Okay, great.
Great. Yeah, contact Professor Kevin Mcfadden, and he will teach you a lot about neutrinos. He's a neutrino expert.
He's actually the spokesperson of one of the neutrino experiments right here.
Yeah.
And
Yeah, we have a section of Minerva in the corridor here. So if you go out just of this corridor, you can see basically a few posters that describe the work that that this experiment is trying to measure these cross sections of neutrinos with different elements. And you have to have a little, a part of that detector in here, in the fourth floor.
So we make very powerful, very intense neutrino beams using accelerators, and then with those neutrinos we can study their properties, which is very fascinating ones. Little guys, little girls, and their properties are very, very different from like electrons, muons, or quarks. So we think that they have some clue telling us something, the origin of the universe. So LSE and Tevatron, these are the accelerators and experiments are doing profounding, hopefully, discoveries, but there are other ones like neutrinos and beams will also tell us a lot about the universe. In fact, you may not have noticed because neutrinos are very, very elusive, and that's why we need a very powerful neutrino beam, very high intensity beam, the spatial detector to study them. So you know that it's elusive, it's because in fact every second about 100 trillion of neutrinos passing through your body every second, but you don't feel anything.
Good thing too.
Good thing too. So that's, yeah, it's very incredible particles.
maybe I'll throw a question out to the group, and maybe Rochester can take a crack at it first. Did you have any indication of neutrinos in your event displays on iSpy? Maybe not directly, but do you have anything that told you that maybe there was a neutrino in the event?
Yeah.
So feel free to come in and then speak up in the laptop.
Yeah, there were actually arrows on that indicated the presence of neutrinos in the reactions. They hear that?
Were you able to hear that?
Not entirely.
Come in.
Nice loud, yeah. There's a microphone
Yeah,
here.
you have to come close to the laptop.
There were actually arrows in the program that showed the presence of neutrinos, so we were able to see if the reactions produced them. That's right.
So arrows, you said,
Yeah.
in the indicated neutrinos. Okay, and what are those arrows referred to in the how are they called in the event display?
Yeah,
The missing energy?
Right,
That's
missing
right.
energy, exactly.
Yeah, we got
Because
your
basically, so CMS does not detect neutrinos, although someone explained to us Wednesday that, well, House Finca actually, that he did the calculation that Atlas should be able to detect 1 neutrino per year. So I imagine CMS is similar. That's not a lot. So we basically don't see the neutrinos, but we can sum up all of the momenta, and what's missing might be a neutrino, and that's what you were seeing, and we're working with. Yep, okay. Any questions from the Notre Dame side?
Are you guys all physics students, or is this a club or part of?
Yeah,
Sorry, right here.
they're all high school students.
Okay,
And all high school?
so all studying physics.
Yep.
Yeah. Okay.
Okay. This gang is actually a physics club.
Cool.
So some have had some physics, some haven't, but they're into it.
What do you do in the physics club?
This.
Well, for the first month, we just we just talked about different like physics, like kinematics and basic.
Physics principles, basic physics, I guess you would say.
Talk about conservation of energy, momentum, just getting familiar with the ideas, and
You
took off from there.
experiment.
Yeah.
Yeah.
It's a cool club. Do other students envy you?
I just had
I've
a
told
fun
people about the physics club. Told them that.
They just ask about it.
Yeah, it's like, oh, what do you do?
Yeah.
That's kind of how that is.
We are cool people.
They've had some fun experiences. They've had some Notre Dame physicists talk with them. They've talked with the control room at Point 5 at the LHC. So.
Right. Hey, Rochester folks, you should create such a club too. It sounds like a lot of fun.
You could have a field trip to Fermilab.
Absolutely.
Gyroscopes.
Oh, right, yeah.
Right, yeah.
That's right. You can also go to Ithaca.
Right, go see Cleo and Caesar.
I have another question. It's a more important question. What was the most interesting part of the experiment that you were doing? Like, because we all had the same information, the same data, but obviously everyone's is a little different. So I guess what was the most interesting part for you guys?
Come in. Sure, yeah.
I found the zoos pretty interesting, just seeing all the different possible, particles that can be created in the collisions, seeing as we don't know, I mean, we personally didn't know what they were, but just all the different paths that can be taken and just all the different variability in the collisions.
Right, so we have one student that found the zoo category the most interesting. You know, all the ones that we couldn't categorize, and they were all exotic, and yeah.
Did you try to get the physicists there to answer when you saw a strange event, to say what they thought it might be?
Well,
You should just jump in here.
Come on down.
Yes.
For the tau, and I mean not for the tau, for the other two that were available from the selection, what was it, the pi naught and the other two particles, yeah, the J psi and the epsilon. For those, we asked them and bought them, and they told us like what those kind of looked like. So then we were able to kind of eliminate those if those kind of signs appeared. But the other ones, not so much. A lot of them just seem to be maybe combinations or both, or there's lots of different mixed kind of signals.
Okay.
The future physicist talking.
Oh, we all are. Okay, so this, we're at the end of our allotted time. If you want to stick around and talk a bit, we can. But if you need to go, that's fine too. So that's up to you. I know these guys are going to take a tour of Fermilab in about 10 minutes, but they'll hang around until then.
You had that one question that you asked them at the beginning.
Oh yeah, the circumference thing.
Yeah.
Sorry? The bonus question.
Yeah, bonus question.
11,000! I've got to come back to you about how many times around the protons go.
11,000.
Did you get an answer?
11,000.
Yeah, they got it right. It's 11,000.
Yeah, we know.
They're yelling.
You guys are better than I am. I usually just round things off and come up with 10,000. Really good.
Hey, science is real.
Yeah, I make 27 into 30 because I can't resist canceling out those threes. Good work. So imagine how many collisions are happening all the time that the software at CMS and Atlas have to deal with. I'm glad I'm not writing that code because I wouldn't know how. Okay.
A lot of effort from all of the world, kind of
Right.
timing, and so making all the combining all the facilities, computing facilities all over the world. It's doing
A
together.
major CMS data center right here,
Right.
just handling all the whatever comes out of the firewalls.
Ken, can I ask you a question, Ken? Ken,
Yes.
it's Friday at Fermilab right now, right?
Yes.
I
Yes.
think so.
How come you're not here?
Yes, we are making a sacrifice.
Yeah, no
Go
wine
on.
and cheese? Where's the wine and cheese?
Let's go that way.
Hour away.
Oh, we're in New York. It's wine and cheese time here.
Well, don't let us stop you, but I think probably we'll keep the students out of that.
Yeah, they're underage.
I like the cheese part though.
God,
You should stick in and eat a cracker.
So are you going to give the students cheese?
Yeah, we gave them cheese earlier. They had cheese. Who likes cheese?
Well, we're close to Wisconsin here, but you're in New York, so you're good.
What time is it over there?
now we're ahead of the time zone.
That's great. That's how I know this.
You guys are jolting back and forth between time zones today.
Yeah. Jet lag.
Car lag.
Right.
Any more questions from Rochester?
Nope, I think that's it.
Okay. Any questions from the gang?
Those are good folks. Yeah.
Okay, well then,
Nice
great afternoon.
Yeah, see you.
You guys are awesome.
So here's the reason why you get 1.4, or why we are actually producing more W pluses than W minuses, okay? And that's just because what we're colliding at the LHC is a bunch of protons with another bunch of protons. And to create a W plus, you need a U and an antiparticle of and the anti-D, basically, okay? So I don't want to get very technical, but also inside these protons and inside these gluons, we can find D bars or anti-Ds or an anti-Us, okay? But the thing is that we don't find them as usual or as often as a U, because of course the proton is made of up, up, and down. So we're very likely to find an up quark much more than a down quark, or 2/3, or 2 times more likely to find a U than a D. And it's also fairly unlikely to then find a D, an anti-D. And if you want to create a W minus, then you need a D and a U bar. And just simply because you have one D and two U's, it is then more likely to produce a W plus than a W minus. Okay? And that's basically the measurement that you see here. This was done last year with CMS data. So basically the same data that you were analyzing. And this is finally the result. So here you see the ones that decay to electrons. And here you do the ratio between W plus and W minus, so how probable it is to produce them, and you see that it's 1.4, the same for W mu, and then when you combine, then that's the point that you get. And this yellow band is the theoretical, so basically what the standard model predicts. Okay? So good job there. We actually got 1.3 in our numbers, so that's actually very, very nice for the amount of events that we actually selected. So that was very good. For example, if you collide things at the tevatron, we are equally likely to produce a W plus as a W minus, because we're colliding antiprotons in this collider at Chicago. And so we have equal amounts of U's and D's, and equal amounts of U bars and D bars on the other. And so we can actually then produce the same rate of W plus and W minus. So at the tevatron, that number is basically 1. So here it all boils down to the fact that we're doing protons against protons. Okay, so that's the reason why we got this 1.4. And then as he was saying, the ratio of electrons and muons should be always 1. So the W and the Z, they don't care what they decay to. They don't have any preference towards an electron and a neutrino, or a muon and a neutrino. Okay? And the same for the plus and the minus. There's no, once you produce a W plus, it has to go to the mu plus. Okay? So anyway, that was my final comment about the physics. So I hope you had a great time, and don't forget you have to fill in, I think, a little question. Don't forget you have to fill in